Hello, this is a video about the Qibec 1-bit 1 instruction transistor CPU that you can see here. This video will be a hands-on introduction to the macro assembler used in this project. And the macro assembler, the function of it is to convert something that is readable by humans, namely an assembly language program, into something that is readable by the CPU, namely a machine code program. To do this, we'll take a bit of a novel approach, namely not start with an assembly language program that is readable by humans, but start with a machine language program that is readable by the CPU and work our way back to an assembly language program that is readable by humans. To do this, maybe it makes sense, maybe it doesn't make sense. The idea behind this is to introduce assembler features that will solve an immediate problem. The problem being that the program is not readable enough. So the hope is that you can appreciate these features more instead of just applying them like a machine, like an assembler, right? So let's try that. Right. Well, let's start out with machine code program in ROM. Let's have one column to indicate the ROM address of each instruction in the program. ROM addresses are 0, 1, 2, 3. And let's have another instruction, another column containing the ROM word at each location. This is 32-bit hex values. I memorized this, hopefully. That's 0, 1. These are all hex 32-bit numbers. Okay, spoiler, this program performs a bitwise OR on a bit given a bit mask. So it takes a bit value and a mask and it applies the mask to the bit. It either sets the bit or it leaves it alone. So remember from a previous video that each ROM word, so each program word, can be divided into two fields, two 16-bit fields along this line. The higher 16 bits are a data address of the bit to invert in this instruction, in each instruction. So for example 0001 would be the data address of the bit to invert in the first instruction. Yeah. The rightmost column is a branch address, which is an optional next program location to jump to. For example, if the bit bit 1 after inversion would be 0, then the next program location would be 2. That's what this instruction says. For details on what the native instruction of the CPU does and what the semantics are, please see another video. That's not discussed here in detail, so I assume you are a little bit familiar with that. Right? This is 16-bit, this is also 16-bit. So if we know that these are two separate fields, we can write it a bit differently. So it's a bit more readable. So let's remove the leading zeros in the fields. Like that. So there's a problem with this, obviously. First of all, each instruction now consists of two numbers. Now, to help in remembering what the instruction does, we can introduce a mnemonic, which is basically a name for an instruction. It tells the human reading it or using the instruction what the instruction does, so it gives a hint to the semantics of the instruction. Now there is only one instruction in the CPU, which is invert and branch if clear, abbreviated IBC. So let's fill it in. It's not very exciting, but now the instruction at ROM address 0 says IBC12. In other words, invert the bit at data address 1, and if it is 0 after inversion, branch to program location 2. Right? So this helps to remember what this does, what the instruction does. Now the next problem is, if you look at the rightmost column and if you look at the leftmost column, you'll notice that both are both refer to program locations. So the leftmost column is the actual program location of each instruction in the program, and the rightmost column are references, consists of references to program instructions. Right? The problem with this is, well, it's not easy to read. You'll have to match numbers. So 2 is there, 4 is there. It's not easy to read. Plus, if you shift this whole program to another location within ROM, this column would change, obviously. And in order to have the program do the same as it did before, this column also has to change. I mean, you will have to change, you will have to add an offset to these numbers. So, to prevent that, you can introduce labels. Now for each reference to a program location, let's replace that program location with a symbolic name. For example, let's look at 4. That would be Z, for example. Let's look at the reference to program location 2, or 3 for that matter. We can write a Y. The names really are, you can pick any name you want, but as long as the reference and the actual program location have the same name. 2, let's pick X. Right. So now we don't need the actual ROM addresses anymore, and instead of the rightmost column being a branch address, it's now a label. So basically this program has become independent of the location within ROM, of its location within ROM. You can do the same for the data addresses. If you introduce constants, for example, constant val of value is 0. This is a bit of tickle programming language. You can replace every reference to data address 0 with val. Now let's do that. You can do the same for a mask. What we do essentially is introduce a variable named val and a variable named mask. So let's replace all the references to data location 1 with mask. The string symbol is an artifact of using the tickle programming language. It is discussed in more detail when we talk about the assembler. Right? So now essentially the data address, the literal data addresses are gone, and you only have named variables. The definition of the variables, I mean the location and data memory, you can store somewhere else. You can put it in a separate file so it's out of the way. Yeah? Now, this is not very readable, so let's look at this piece of code. If you remember that, and the semantics of the instruction are invert this bit at mask, and if that bit is 0 after inversion, jump to Y. So what you see is the bit at mask is inverted. If it is 0 after inversion, go to Y, which is the next address. If it is not 0 after inversion, also go to Y. So essentially this swaps the bit, this inverts the bit unconditionally. Now this is difficult to read. You have to think what it does, and that can be troublesome when you have to read through a whole program. So let's introduce something called a macro, which is a named piece of code basically. Macro in this case name is not. Something like that. So this basically says whenever the word not is encountered in the program, the assembler would replace that word with the code inside the macro body. So now we can write, instead of this, oops, not mask. So it is as if we have a new instruction called not. The definition of not, you can put it in a separate file, you can put it out of the way, we don't need it anymore. You can do the same for this code sequence. So if you look at what this does, it inverts the bit at val. If it is 0 after inversion, go back to y. Y is the previous program address, so it would execute the instruction again. Invert the bit at val again. If it is 0 after the second inversion, then go back. Actually, if you invert a bit twice, either after the first inversion or the second inversion, the result will be 1. In case it is 1, this instruction will continue at the next program instruction, which is Z. Okay. So basically this sets the bit unconditionally. Now we can write another macro named set that does exactly that. And by doing that we basically introduce yet another pseudo instruction. Now let's call it here again. Now, okay, so whenever set is encountered in a program, the assembler will replace that name with the body of the set macro. Note that this reg for register is like a placeholder, so whatever is passed, in this case for example mask, whichever is passed to the macro is filled in place of reg. So we can replace this code with this. Right. The macro body you can move out of the way into a separate file. We don't need it now. It's obvious what the code does. We don't need the implementation of the macro anymore. Now you see that the label Y that was just here is gone. It's not referenced anymore. It's not needed. So the code becomes simpler all the way, all the time. Now you can simplify this more, but what you can also do is you could probably read through this. What you can do then is introduce a macro named OR, which was the function of the original program, which takes two parameters, namely val and mask, and does exactly that. So now instead of writing this, the green code, we can write simply OR simply write that. Once again we can move the implementation of the macro in a separate file. It's not needed anymore. Now, so this is much simpler than, much easier to read than some hex words, I think. So that's basically how it works. So I hope you enjoyed this video. I hope it did make some sense at least, and please watch the other videos. Let me know what you think. Please visit the Qibec site, that is qibec.org, for more information on the CPU, and see you in another video. Thanks for watching, goodbye.